The information covered in these notes is a continuation of Chapter 14, Section 1. And in that section, there's a lot of information about chromosomal genetics, but in it, there is a section on pedigrees. And so that is what the theme of today's notes is. So starting at the very beginning, a pedigree chart is a presentation of family information in an easily readable picture form. And we probably want to mention that it's a genetic family tree. So you can look at the inheritance of a particular trait followed through several generations. Now, to begin, we have to talk about the symbols that are going to be used in a pedigree. So I'm going to actually go over to the left over here and talk about what the symbols mean. And then I'm going to walk you through how to fill out a pedigree. So first of all, when we talk about these pedigrees, you're following a trait through generation to generation, and it's genetic. So you're looking at the passing of alleles from parent to offspring. And so the circles are going to represent genetic females, and I'm going to draw the female symbol there. And squares are going to represent genetic males. And if you have a filled in symbol versus a non-filled in symbol, it's going to mean something a little bit different. A filled in symbol means they have the trait, whatever the trait that we're looking at is. If the symbol is not filled in, they do not have the trait. They are not exhibiting the trait phenotypically. Couple of other things you need to know. If you see a line in between symbols, it makes a difference how that line is depicted. If the line connects a male and female, it's going to represent a mating or marriage. So they will possibly have children or be married. If the symbol is connecting the tops, if the line is connecting the tops of the symbols, sorry about that, this means siblings. So the goal is that you are trying to solve the pedigree by filling in everyone's genotypes. And then often you are answering associated questions once you have filled out everyone's genotypes. A couple of other reminders: if you have an autosomal pedigree, it is on chromosomes 1 through 22, not on the sex chromosomes. And if the trait is sex-linked, it's on chromosome pair 23. So it is on the sex chromosomes. The trait is found on the sex chromosomes. So you typically want to look at the prompt to determine what type of trait you're dealing with the pedigree. Is it autosomal or is it sex-linked? So A, B, and C talk about ways to go about solving the genotypes for the individuals. So starting with letter A, start by predicting the genotypes of the recessive individuals. Their genotypes are completely known. Predict the allele of an individual that displays the dominant form of the trait next. And then what you do is you then look at children, essentially, to determine, backtrack and figure out what the second allele is. And so the best way to show you is to actually do a problem, and doing it helps to explain how to solve them. So the one that we're going to do first is this one down below. Analyze the following pedigree. Again, solve by filling in everyone's genotypes. If the second gene cannot be determined, place a dash next to the dominant gene. I'll explain that in a minute. Begin with the recessive individuals. This pedigree analyzes tongue rolling. So it's when you make your tongue into a tube, kind of like a hot dog bun. That's tongue rolling. And it is autosomal dominant. So they tell you what the trait is in the prompt. They say big R is someone who can roll their tongue and little r is someone who cannot roll their tongue. Also, again, remember, if they're shaded in, they have the trait. If they're not shaded in, they don't have the trait. So we're going to start with our non-rollers first because they are little r. We know their genotype completely, and we can easily go fill them in. Our non-rollers are not shaded in. So that's number 6, number 9, number 10, number 14. Now, what you would do next is then fill out everybody else can roll their tongue. So they have at least one big R. So you can put one big R for everybody who's remaining. And now the hard part is figuring out what is the second allele for each individual. Sometimes you can figure that out pretty quickly. Other times you might not be able to determine it. So here's an example. Number 6 is a female. She is homozygous recessive, and she is the daughter of 1 and 2, and that means that both 1 and 2 had to have given her a little r for her to be a non-roller. So I use the daughter here as a way to backtrack and figure out what the second allele is for both 1 and 2. I failed to mention, and I'm going to mention it now, that the generations, P, F1, F2, that you're familiar with when we talked about genetics initially are listed off to the left. So these are the parents, these are their offspring, and F2 would be like their grandchildren, and here we even have an F3 generation, which are the great-grandchildren. Where is another example of how I can use the little r's to backtrack and figure out parents? Another example is here, 9 and 10. 9 and 10 both are homozygous recessive. Their parents are 3 and 4. The mother must have a recessive allele, and the father must have a recessive allele. So we're making our way here. Let's see if we can find other places that we can, again, use the offspring to figure out the parents. Well, here I have number 14, homozygous recessive, son of 11 and 12. That means that 11 must be heterozygous and 12 must be heterozygous. Now let's take a look at who is left. 7 and 8, 13 and 15 are the only people that we have not identified. I'm going to start with 7. 7 is the son of 1 and 2. Unfortunately, 7, we know that 7 and 8 have a son that's heterozygous, but we don't know which parent, if not both of them, are heterozygous that passed on that recessive lowercase r. This is an example of where you'd put a dash. We don't have enough information to be able to determine who has what second allele. So a dash is acceptable as long as you are sure that you cannot figure out what that second allele is. For example, if you put a dash here, that would be wrong because you know that 14 is homozygous recessive and inherited one small r from each parent. So you can't put dashes where they don't belong. Let's go to 13 and 15. Again, 11 and 12 are both heterozygous. And, 13 might be heterozygous, but they also might be homozygous dominant. We don't know. So here's another example of where we would put a dash. Again, the dash means that we just don't have enough information to determine what the second allele is. So this is an autosomal pedigree. And this one happened to be a dominant trait. The next page has another type of pedigree. This is a sex-linked pedigree. So they say in the prompt it's sex-linked. And again, you have to identify the genotype, so that's solving the pedigree. They also want you to include proper notations for males and females. I'll show you how to do that. If you find a female to be a carrier, place a dot inside her circle. That's going to help us denote that she's a carrier. And we are going to find everyone's genotype for this particular pedigree is color blindness. So this follows the color blindness gene in a family over 3 generations, the parental generation, the F1, and the F2. They want us to use the allele letter N. So capital N is a normal allele and a lowercase n is a colorblind allele. And so anyone who is colorblind is going to be recessive. Anyone who has normal vision, not colorblindness vision, is going to be capital N. Now, what you need to do is start by writing everyone's sex chromosomes for a sex-linked pedigree. So I'm going to write that as number 1 down here. Write everyone's sex chromosomes. Males, genetic males, are going to be XY. Genetic females are going to be XX. And I apologize, the lines are very small. So do your best. Now, doing this is just setting us up to solve the pedigree. We are really not even doing any heavy thinking here. We're just writing everyone's sex chromosomes based on their symbol. I'm going to change colors so you can follow the alleles. Let's do red. So number 2, start with the males, because they only have one allele that we need to worry about. So for example, and again, remember, if the symbol is shaded in, they have the trait. So that means shaded in symbols are going to be colorblind. Non-shaded in symbols are not colorblind. Well, who's colorblind in this pedigree? Number 6, number 11, and number 16. So number 6 is a male. He's colorblind. He has a little n on his X. He does not have a color blindness allele on his Y. So again, remember, don't put the allele on the Y chromosome. Number 11, same thing. Number 16, same thing. So with regards to the genetic males, do the recessive individuals first, then do the dominant ones. So all of the remaining males must be capital N because they're not colorblind. So number 2 is going to be X big N Y. Number 4 is going to be X big N Y. Number 8, another genetic male, not colorblind. Number 12, number 15. And I think we have all the males solved. So number 3, then move on to the females. In this particular pedigree, we don't have any recessive individuals. So I have recessive individuals next because if we had any shaded in females, they would also be pretty easy to solve because they would be X little n, X little n. We don't have any females that are colorblind in this pedigree. So we then need to move on to the dominant individuals. All of the remaining females are not colorblind, so they have at least one big N. So I'm now going to go for the first X for all of the remaining females and fill out a big N. And now we just have to figure out the remaining second allele. So use the offspring. Oops, that's supposed to be a G. To determine second allele. So how are you going to do that? Well, remember that fathers give the Y chromosome to their sons and women give the X chromosome to their sons. So for all of the boys, remember that the X chromosome came from their mother. That's helpful because, for example, number 6, this Y chromosome, and I'm going to change colors again, came from the father to his son, which means that this little n, and number 6 is the son of number 1, must have come from his mom. So that means that number 1 is a carrier for color blindness. She passed on the little n allele to son number 6. Now they also said they wanted us to put a dot inside her circle, so I'm going to do that. That kind of signifies that she's a carrier. And then we're going to move on and see if we can figure out any other second alleles. Number 3 also has a son who's colorblind. Number 11, similar situation. The Y chromosome came from dad. That means that the X with the colorblind gene must have come from mom. So she is also a carrier. And again, I'm going to put a dot inside her circle. I'm going to get rid of these arrows too so they're not in the way. What about number 5? 5 is the daughter of 1 and 2. She has a big N, but she's a girl, and fathers give their X chromosomes to their daughters. So we're going to assume that this X big N came from dad, and so now we have the other X chromosome that needs to have come from mom. But mom could have given, number 1, could have given number 5 a big N, or she could have given her that little n. And number 5 doesn't have any children to help us try and deduce what that second allele is. This is an example of where you put a dash with the sex-linked pedigree. If you don't know the second X chromosome's allele, you may put a dash. Let's move on to number 7. Number 7's over here. This is the wife of number 6. Number 7 is not the daughter of 1 and 2. She's the wife of number 6. Number 6 and number 7 also have a son that's colorblind. This is interesting because students will often get tricked up in that they think that that color blindness gene was passed from father to son. But remember, fathers pass their Y chromosome to their sons. So that means that this colorblind allele came from mom, number 7. That means that she is a carrier. And again, we're going to put a dot inside her circle. And just to show you that this Y came from dad, this X came from mom. We're almost done. Back to red. Let's take a look. We have 1, 2, 3, 4, 5, 6, 7, and 8 solved. We're now just on the F2 generation and we have to fill in who's missing. So now we're on to 9 and 10. They are sisters, and they are the daughters of 3 and 4. Dad must have given them both this big N. Mom could either give a big N or a little n, and neither 9 nor 10 have children for us to try and deduce that second X chromosome. Another example of where we'll put a dash because we don't know what that second allele is. 11 and 12 are solved. Now we're on to 13 and 14. 13 and 14 are the daughters of 6 and 7. They both do not have color blindness, but if you look at their parents, the big N came from mom because dad has a little n on his X chromosome, which means that mom gave them both the big N, and dad must have given them both the colorblind allele on his X chromosome, which means 13 and 14 are both carriers. So again, dot inside their circle, they carry the colorblind gene, and we have solved everyone's genotype. Again, if you have a pedigree, you'll often have questions associated with the pedigree. So not only would you need to solve it, but you might be asked, what's the relationship between 6 and 5? And you would need to be able to look at the pedigree and say, oh, well, they're brother and sister. What's the relationship between number 2 and number 13? Well, number 13 is the daughter of 6 and 7, and number 2 is the father of number 6. So what you would say is it's the paternal grandfather. And what I mean by that, it's the grandfather of 13 on her father's side of the family. So that's also, if you ever see maternal, it means on the mother's side. And paternal means on the father's side. And that is it. So we've just gone over sex-linked pedigrees and autosomal pedigrees. A reminder, autosomal pedigrees are on chromosomes 1 through 22, not involving the sex chromosomes. And sex-linked pedigrees, like on the second page, are found on the 23rd pair, the XX or XY. And that is it.